We are in Chapter 9, Differential Equations. Section 9.1 is Modeling with Differential Equations. In Chapter 1, we introduce the process for modeling, and that is a mathematical model of real-world problems through intuitive reasoning or from a physical law based on evidence from an experiment. A mathematical model often takes a form of a differential equation, and this is very useful, especially in engineering, and an equation that contains an unknown function and some of its derivatives, and that by definition is a differential equation. In many real-world problems, we often observe the changes that occur, and we want to predict the future behaviors on a basis of how current values change. So, order of a differential equation is the order of highest derivatives and that occur in that equation. So for Math 181, we deal with first order differential equations, and we're going to just abbreviate differential equations by DE. They also call it ODE, and you will take courses on this for certain majors that are just on differential equations. And so next thing says a family of solutions is a general solution. For example, if we had y equals x plus c, where c is any real number, and then we have an initial condition, which would be at time 0. And this would be y of t sub 0 is equal to y naught. And we have an initial value problem. This is a problem of finding a solution of the differential equation that satisfies that initial condition. So the first thing that we're going to look at is a population growth model. And we're going to say let t equal time and p equal the number of individuals in the population. Then the growth rate of the population is going to be dp dt. Then the rate of growth is proportional to the population size. So dp dt is equal to k times p, where k is the proportionality constant. Note, eliminate the possibilities of a population of 0. Then p of t is going to be greater than 0 for all t. If k is greater than 0, then the population of t will be greater than 0 for all t, which implies that the population is always increasing. Thus, the growth rate increases as the population increases. So we're going to let p of t equals c times e to the kt, and this is back from chapter 3. Then, taking a derivative of this, we would have c, which is our constant, times the derivative of e to the kt, which would be ke to the kt. And this would also be the same thing as k times c e to the kt, which again, this right here is equal by definition as we defined it as p of t. So this is k, p times t. Now graph the family of solutions for p of t. And so as we increase, since this is an exponential, this would increase. But again, it depends on those constants, and so it could also be maybe a little bit higher, even more higher, the flip of this, a little lower. And so these are the family of curves that could be solutions for p of t. So we are only concerned when c is greater than 0 and when t is greater than or equal to 0. So when t is equal to 0, though, this is the initial value. So the initial value would be our population at time 0 would be equal to, if you substituted in 0, that would just be equal to c. And this is the initial population. So the initial population. Many populations start by increasing at an exponential manner, but the populations level off when it approaches its carrying capacity m, or decreases towards m if it is overexceeded m. And so two assumptions that we have, one is going to be that our derivative d of p dt, so the derivative of the population with respect to time, is going to approximately equal k times p. So if p is small, and this is going to be the initial growth rate is proportionate to p, and then also dp dt, again that growth rate of the population with respect to time, is going to be less than 0 if our population is greater than that carrying capacity, which we defined as m. And so this would be p decreases if it over exceeds m. So if it's too large. A simple expression that incorporates both assumptions is given by the equation. So dp dt is equal to k times p times 1 minus p over m. If p is small compared with m, then p over m is close to 0, so dp dt would be equal to k times p, like we stated up above with our assumptions. And then if p is greater than m, the 1 minus p over m is negative, so dp dt would be less than 0. And so thinking about this in terms of a graph, if we had our time here and we could say m is going to be our carrying capacity, means that our populations would increase towards that carrying capacity and have that family of curves here, or it could be decreasing if it exceeds the carrying capacity. So again, dp dt is less than 0 if p is greater than m, and dp dt is going to be greater than 0 if our population is greater than 0 but less than m, which is that carrying capacity. So then it would be increasing. So to verify a solution to a differential equation, first take the derivative of the solution, then substitute it into the differential equation and verify that both the left and the right sides of the equation are going to be equal. And then you also will have to check any initial conditions that you might have. So the first example on here says verify that y equals negative t cosine t minus t is a solution to the initial value problem t times dy dt equals y plus t squared sine of t. And then we also have an initial condition over here that we need to check. So the first thing that we're going to do is first take the derivative of the solution and then substitute it into the differential equation to verify that both the left and the right sides of the equation are equal, which is stated right up above. And so we need to find dy dt. And taking the derivative of our solution, which was y equals negative t cosine t minus t, we're going to have negative t times the derivative of cosine of t is going to be negative sine of t. And then the derivative of negative t is negative 1 times cosine of t, so using that product rule there. And then minus t, so the derivative of minus t would be negative 1. So simplifying this, we have t sine of t minus cosine of t minus 1. And we're going to take this and substitute it in to the initial value problem that we had. And so doing that, we arrive at t times dy dt, which is t sine of t minus cosine of t minus 1, is equal to y plus t squared sine of t. And so doing this, we have t squared sine of t minus t cosine of t minus t. And checking to see if this is going to be equal to y plus t squared sine of t. And so we can see the part that's boxed, which is negative t cosine t minus t, which is the same thing as what was given to us, is equal to y. And so this would be t squared sine of t plus y is equal to y plus t squared sine of t. So check, that does match. And so what we did was we took the derivative of the solution and then substituted it into the differential equation, and we just verified that that left and that right side of the equation are equal. And we also need to check that initial condition. And the initial condition that we had was y of pi which is going to be equal to negative pi cosine of pi minus pi. And cosine of pi is going to be negative 1. And so we get pi minus pi, or just 0. And so we say check, that works. Y of pi here is equal to 0, which is what we were trying to verify. So yes, this is a solution to the initial value problem that was given. So the next example that we have says, Part A, show that every member of the family of functions y equals ln of x plus c over x is a solution to the differential equation x squared y prime plus xy equals 1. So the first thing is that for this problem, it's not written as dy dx, it's written as y prime. Same thing, that derivative. And so we have to go ahead and take a derivative of y. And so to find y prime, or dy dx, we're going to take a derivative of y, which is given to us up above. And so we have to use that quotient rule. And so the quotient rule is going to be the bottom, which is x, times the derivative of the top, which is going to be 1 over x plus 0, just 1 over x, minus the top, times the derivative of the bottom, which is just 1, all over the bottom squared. Simplifying this, we get 1 minus ln of x minus c all over x squared. And so now we need to take our derivative and substitute it in for our y prime that we have up above into the differential equations solution. And so doing that, we have x squared times y prime, which is 1 minus ln of x minus c, all over x squared, plus xy is equal to 1. And so we need to work this out, but I also notice that I have a y in addition to just x's. And so we also know that y was given to us up above. So I'm now going to substitute that in also. And so simplifying this and also substituting in y equals ln of x plus c over x, I get 1 minus ln of x minus c plus x times y, which is ln of x plus c over x is equal to 1. And again, those x's reduce. You're going to also have your c's reduce, your ln of x reduce, and we do just get 1 equals 1, so check. So we did just verify that that derivative of the solution is a solution to that differential equation by verifying that the left and the right sides are equal once we substituted that in. And then the next part, part B, so this was our part A. Part B says find a solution to the differential equation that satisfies the initial condition y of 1 is equal to 2. And so in order to do this, we need to, so part B is y of 1 is equal to 2. And we know y of 1 is equal to ln of 1 plus c over 1, which needs to equal 2. And so solving this, ln of 1 is just 0. And so we get c is equal to 2. And so our solution to the differential equation is going to be y equals ln of x plus c, which in this case is 2, all over x. And then part C says find a solution to the differential equation that satisfies the initial condition y of 2 is equal to 1. And so for part C, the initial condition we have is y of 2 is equal to 1. So y of 2 is equal to ln of 2 plus c all over 2 has to equal 1. And going ahead and solving this, we get ln of 2 plus c is equal to 2. Or we can say that c is equal to 2 minus ln of 2. And so this means that substituting this in, we get y is equal to ln of x plus c, which is going to be 2 minus ln of 2 all over x. The example says a population is modeled by the differential equation. The derivative of p dt is equal to 1.2 times p times the quantity of 1 minus p over 4,200. Part A says for what values of p is the population increasing? And so for part A, if it's increasing, that means that that rate is increasing or that derivative is increasing, so that dp dt would be greater than 0. And so we know that dp dt is equal to 1.2 p times 1 minus p over 4,200 is going to be greater than 0. And we would assume that p is greater than 0 since it is a population. And so we'll say assume p is greater than 0. And this means that the 1.2p is already going to be greater than 0. So that means that that second factor here also has to be greater than 0. And so we have 1 minus p over 4,200 has to be greater than 0. And this is the same thing as saying that if you added the p over 4,200 to the other side, that 1 has to be greater than p over 4,200. Multiplying both sides by that 4,200, we know p has to be less than 4,200. So therefore, the population is increasing when p, which is defined as being greater than 0, is also going to be less than 4,200. So part B says, for what values of p is the population decreasing? So again, likewise, decreasing, our derivative would be less than 0. And so for this, we know that it is less than 0. Looking at what we have above, it's decreasing when our population is going to be greater than that 4,200. And so therefore, population is decreasing when p is greater than 4,200. And then part C says, what is the equilibrium solutions? And so this equilibrium solution right here, anytime we see equilibrium, is going to be where we don't have any growth of the population increasing or decreasing. And so this would be when dp dt would be equal to 0. So dp dt is equal to 0. So where it's at equilibrium, it's not increasing, it's not decreasing. And so that means that 1.2p times 1 minus p over 4,200 would be equal to 0. And so solving this, we're either going to get this first part here that p is equal to 0, so we have no population, or solving the second one, p is equal to 4,200. So we'll say, therefore, we have population equilibrium, so equilibrium solution when, and we'll say when p is equal to 4,200. Since when p is 0, we don't have any population. So right below this, we have another example to look at that I'm going to go ahead and circle, and we'll work on that one together in class.